In this problem, we're given the waveform for the current flowing through a 1 nanofarad capacitor. If the capacitor has initial voltage of 5 volts at t equals 0, determine the waveform for the capacitor voltage, how much energy is stored in the capacitor at t equals 6 milliseconds. Now, we're given the current waveform and asked for the voltage, so we're going to use V of t, 1 over c, integral from 0 to t, I dt, plus an initial voltage. Then we need to go in and describe the waveform over different intervals. Then we're going to apply this expression to be able to determine the capacitor voltage. Once we have the voltage, we're going to come back and calculate the energy. So let's start first by describing the current waveform over the interval 0 to 2 milliseconds. Straight line, so we have y is equal to mx plus b. We know the y-intercept is 0 here. Our slope is 0 minus, or minus 10 microamps minus 0, and it does that in 2 milliseconds. So we've got minus 5 times 10 to the minus 3. So our current waveform is minus 5 times 10 to the minus 3 t amps. Now, the next couple of intervals are pretty easy, because really all the other intervals are easy because they're constants. If we look here from 2 to 4, it's minus 10 microamps. From 4 to 5, it's 0. From 5 to 10, it's 10 microamps. So we really won't even go to the trouble of writing those down. We can just look at the waveform and see, okay, then that's constants. So if we want to start calculating here, so from between 0 and 2 milliseconds, our expression is V of t is 1 over c. Well, that's a nanofarad. That's 10 to the minus 9th. Integral from 0 to t, minus 5 times 10 to the minus 3 x dx. And the initial value is minus 5. So, if we pull out this term, this will have minus 5 times 10 to the 6th out front, integral from 0 to t, x dx, plus or minus 5. And if we integrate and plug in the limits, this becomes minus 2.5 times 10 to the 6th t squared minus 5 volts. So that describes the voltage. Now, we know the waveform changes at t equal 2 milliseconds. And what we need to do is this describes the voltage between 0 and 2 milliseconds. Now we know that the voltage across that capacitor is continuous. So let's calculate V of t is 2 milliseconds. We want to know what is the value of the voltage at the end of this interval, because that's going to be the value of the voltage at the start of the next interval. So we have minus 2.5 times 10 to the 6th times 2 times 10 to the minus 3 squared minus 5. And if you calculate that, V of t is minus 15 volts. Okay, so then V of t is minus 15. That's going to be, for instance, like our initial value for the next interval. And if we look at the next interval, we can see, for instance, that the current is a constant at minus 10 microamps. So, between 2 and 4 milliseconds, we know that the current's constant at minus 10 microamps. So now we're going to have V of t is 1 over c, 1 over 10 to the minus 9. The integral from 2 times 10 to the minus 3 to t of minus 10 microamps. And this is minus 15 now. This came from the calculation for the previous interval. That's our initial condition for this interval. So we put minus 15 in there because that's the voltage across the capacitor at 2 milliseconds. So now we have minus 10,000 So if we integrate and plug in, here's our expression for the voltage. Now, at the end of this, at 4 milliseconds, the waveform changes, so we need to calculate the voltage at 4 milliseconds. So if we plug in then this gives us V of t at 4 milliseconds is minus 35 volts. Now we're going to use that as a next for the next interval now, but if we look, the current's 0. Okay, so if we think about this term here, there's going to be 0. So also we can state that V of t at 5 milliseconds is also going to be minus 35, and that's because there's no current flowing through the capacitor during the interval from 4 to 5. Now, if we look at 5 to 10, we can see the current now is constant at plus 10 microamps. So between 5 and 10, we'll have V of t 1 over c, and then we'll have the integral from 5 times 10 to the minus 3 to t, 10 times 10 to the minus 6 dx minus 35. So now we have 10,000. We have the integral and if we integrate and plug in, now we get 10,000 t minus 5 times 10 to the minus 3 minus 35. And if we note, we need to now calculate what's the voltage at 10 milliseconds, because then the current goes to 0. So now we have 10,000, we've got 10 milliseconds minus 5 milliseconds minus 35, and this gives us 15 volts. Okay, now current 0, so there's no change in the voltage. So now let's sketch our voltage waveform. And here's V of t in volts. It starts off at -5, and then by the time we get to 2 milliseconds, it's down at -15. Now this is a parabolic waveform. And this is, remember, this is waveform is a t squared. Now, if you remember, that's because we had a ramp. Now, remember, out to 4 milliseconds, then we go down to -35. Now, this is a linear. Okay, this part of the curve is linear because we've got a constant current. Now it stays at -35 for 1 millisecond. Then it starts coming up. Okay, and by the time it gets to 10, it's up at 15. Okay, so now, okay, this is again linear. Okay, so there's our waveform. Now we've got one last thing to calculate. Is we wanted the energy stored in the capacitor at t equals 6 milliseconds. Okay, so on our plot, here's 6 milliseconds. So we got to calculate that voltage value. So now we know between 5 and 10 milliseconds that the voltage is given as this. So at t equals 6 milliseconds, so we get V of t is 10 minus 35 minus 25 volts. And if you remember, the energy expression for a capacitor is 1/2 CV squared. So we have 1/2 times 10 to the -9 times minus 25 squared. So that says it's 0.3125 microjoules, or we could write it as 312.5 nanojoules. So here's at t equals 6 milliseconds how much energy stored.